Okay, this lecture we're going to look at the investigation of a factor group and just look at some questions. So the set we're going to use is as follows. It's a 3x3 matrix group where A, B, and C are elements of the integers. So this is a group under matrix multiplication. And you can use the same proof from homework 2. Where these elements were real numbers. If you look through that proof, there's no way that you take the inverse of A, B, and C of those numbers. So it would work equally well for numbers in the integers that didn't have inverses. And G is sometimes called the Heisenberg group. And then given P at prime, let N of P be the subset of G, where we're looking at all multiples of P. And we claim N of P is a normal subgroup of G. That's what that triangle means, that it's a normal subgroup of G. So first of all, we have the identity. Is in N of P. So N of P is not the empty set, right? Because we can take A, B, and C. 0 is an integer. So it could be written in that form. Now let's take two elements. If we take one element in N of P and a second element in N of P, which I'll put the primes there. And the inverse of it. I've given a long, detailed calculation, and maybe I'll show an intermediate step. Again, this is still N of P, and then P inverse would be PA prime, PB prime minus PC prime. And when the dust settles, you end up with 1P times A, or if you will, negative A prime plus A, 0, 1, P times negative B prime plus B, 0, 0, 1. And then our final entry is just going to be, after some factoring, we can pull out P, A prime, B, P, B prime, minus C prime, minus A, B, B prime, plus C. And yeah, that should see, that should do it. And so again, you see these are integers here, so each of these three entries are a multiple of p, so this is an element of n of p. So we've shown it's not empty, so by the one-step subgroup test, we have a subgroup of G. This set NP is a subgroup of G. Again, that's because an arbitrary element in n of p times the inverse of another second arbitrary element ends up being in the set n of p. Okay, so what about normal subgroups? So, well, remember, recall we've got an alternate definition at the end of the last lecture of what an of a subgroup, of how to tell a normal subgroup. Rather than directly looking at left and right cosets, we have to just show that what? To show n of p is normal in G, what do we need to show? Well, let me just say element-wise, and then we'll go to the matrix. Element-wise, we need to show for all n and np, for all G in G, G inverse NG is an element of NP. Right, recall, remember, the way to show NP is normal for all G in G, G inverse times the set N of P times G has to be contained in N of P. So that's how you show it element-wise. So let's see why this is the case. If we look at one element, and I'll use x, y, and z, times the typical element of the inverse of the typical element of the group, times an element in the set. Again, I labeled this as C instead of B, but the point is we've got P times a number, B times a number, C times a number, and then again that typical element itself. And so this is, all of the letters are integers. And you go through and you do a long calculation showing many steps. And it turns out you would get 0, P of A, P of A, Z plus B minus CX, P of B, 1, 0, 0, 0, 1. So that's your matrix, and that's an element of N of P. Thus, for all G in G, G inverse N of P G is contained in N of P, so N of P is a normal subgroup. First we show it's a subgroup, then we show it's normal. So what does that tell us? Anytime we have a subgroup that's a normal subgroup, the collection of cosets then become a group called a factor group. So let's look at some things. So G of n mod p, which again is a set of all G and P, where G is in G, is a group. under multiplication of what I called last class, or a couple classes ago, lectures ago, multiplication of complexes, set multiplication. And so first question is, how many different cosets are there? And we'll return to this. There's no easy answer just right off the bat. N of P is has infinitely many elements. G has infinitely many elements, so it's possible there might only be finitely different cosets. That would still be enough to give us infinitely many elements. It's possible there could be an infinite amount. So we'll go about this. Another question is the cyclic. Well, any cyclic group must be abelian, so let's first see if it's abelian. If it's not abelian, we can conclusively answer, no, that factor group is not cyclic. If the factor group does end up being abelian, there's maybe a chance. So let's look at this, and let's try to show this. And so I'm going to do this. I'm going to show it's not abelian. So I'll try to do that. That's easy. I don't have to do the general proof with arbitrary elements, of the set. I can just show an example of two cosets that don't commute. So let me first look at multiply these two cosets. And again, the way you multiply cosets, you would multiply these two representatives, and we end up with 1, 1, 0. And then we'd end up with 0, 1, 1, 0, 0. And then on the other way, let's look at if we multiply in reverse. We would get the coset determined by, that would be a 1, 0, 0, 0, 1, 1, and then 0, 0, 0, 0, 0, 1. So are these two cosets equal? Now remember, we can't just say, well, this is different than that. Just because two representatives are different, they may still give us the same coset. So how do we check that? What we need to do is let's test that. If it's equal or not, then that's got to be that 1, 1, 0, 0, 0, 1, 1, 1, 0. The inverse of 1 times the other would have to be in the set itself, N of P. So that's how we can tell if these two cosets are equal. So if we make this calculation, you end up again shortening some of the step-by-step that I've provided in the notes. You actually take the inverse and multiply them out. You would get this. which is certainly not an n of p because, for instance, you look at this, if p is a prime number, p can't divide 1. Maybe I'll say that in words. 1 is not a multiple of p. So that means this inverse times that element is not an NP, so the coset determined by this element is not the same as the coset determined by that element. And I'm not putting through the details of the of the step-by-step account that calculation, how you would get the inverse of that. Let's see. And maybe I should, because I'm not sure if this is correct. Let's see, inverse. That would give us this. So anyway, you'll get that matrix is not in N of P. We'll have to go back and look at this product here, make sure this is correct with this. But in any case, you do not get a, that product of the inverse of 1 times the other is most definitely not in P. Or what was, I think, and so that's why 2 of them are equal. In fact, let me pause the video now. We'll return to this in a second.